Machephy Eduworld.
Good morning, students. So, Mehul, are you here? Can you hear me?
Yes, sir.
Okay. So, in the previous class, we were studying about the Earth's magnetic field, and we studied about two angles. We're going to first learn about them in details, and then we'll do some problems based on it. So, there are two angles. First was angle of declination, and the second was angle of dip. So, if you want to visualize them, so angle of dip is basically if this is the surface of Earth. So angle of dip is easy to visualize. This is Earth's surface, and Earth's surface के horizontal से जो magnetic field line का angle बन रहा है. This is the magnetic field. So this is angle of dip. This is angle of dip. Horizontal. This line is horizontal. So this angle is called angle of dip. And angle of declination are represented by capital D. Angle of dip are represented by small delta. And angle of declination, that is, on globe there are lines. Those lines are called geographical meridians. But our magnetic field, it is making some angle with it. Suppose it is like this. So यहाँ पे angle बन रहा है D. This is angle of declination. यहाँ पे angle बन रहा है D. This is angle of declination at this point. यहाँ पे angle बन रहा है D. So this is angle of declination at this point. So angle of declination is the angle with the geographical meridian. These lines are geographical meridian. What is geographical meridian? जो ग्लोब्स पे लाइन बनाते हैं फ्रॉम नॉर्थ पोल टू साउथ पोल, दैट इज जियोग्राफिकल नॉर्थ पोल टू जियोग्राफिकल साउथ पोल, those are called geographical meridian. And another way to visualize this is to represent it via planes. So suppose I have two planes. First plane is your, this plane represents, this direction represents geographical north. Okay, so this is horizontal to the surface, and I have another plane which is pointing towards magnetic north. I'll draw this plane so it will look like this. Okay, so angle between the geographical north and magnetic north, that angle is angle of declination, capital D. And let us say the magnetic field is in this direction. Means it is not horizontal, it is pointing towards downward direction, like this. So it is in this plane. I'll mark this plane as ABCD. ABCD is the plane in which our magnetic field direction is from C to A. And ये magnetic north, this is also horizontal. Horizontal के below जितना जाएगा ये magnetic field का direction. This blue arrow shows magnetic field का direction. These magnetic field. Horizontal के जितना below होगा, that is the angle of declination. Okay. Suppose magnetic field का value is B. The net magnetic field is B. Okay, or let me write it as B, that is magnetic field of Earth. तो इसके दो components ले सकते हैं. One along the horizontal. So magnetic field along the horizontal. along horizontal, that is called BH, that will be BE, magnetic field of Earth, into cos delta. And magnetic field perpendicular to Earth surface, I'll call it as BV, that is vertical magnetic field. This is vertical direction magnetic field. This will be component of this and the along the direction of CV. So ये delta है तो 90 minus delta हो जाएगा. So this is BE sin delta. So these are the horizontal and vertical component. If you want to write, you can also write tan delta. Tan delta is horizontal component, no, vertical component by horizontal component. This results in our delta as tan inverse BV by BH. The delta is angle of declination, no, angle of dip. Dip is going downwards, dipping down.
Sir, so angle of dip is angle between Earth's surface and magnetic needle, right?
Earth's surface and magnetic field, yeah. Horizontal or Earth's surface, I mean, horizontal or magnetic field direction, each direction. Okay, suppose I want to find the component of the magnetic field along geographic north. Then I can take the component of this angle, magnetic field of magnetic north to the geographic north. बस इसका component लेना है geographic north. So magnetic field along geographic north, that will be magnetic field along magnetic north into cos of T, cos of angle of declination. So magnetic field along magnetic north, that will be BH. So this is BE cos delta. So BE cos delta into cos T. That is the magnetic field along geographic north. Let's do some questions now.
Sir, I am noting.
Okay, okay.
Sir, small d is S, right?
Small d is your delta. That is the angle of dip. For the first one, can you tell me the answer?
Sir, I got 5 root 3 into 10 to the power minus 5. Horizontal.
For horizontal. Okay. That will be BE cos delta. No? So 5 root 3 into 10 raised to minus 4. What is the value of BE, that BV along the vertical?
Sir, it will be 5 root 3. The BH is 5 root 3 into 10 to the power minus 5.
Yeah.
And BV is 5 to 10 to the power minus 5.
Okay. And magnetic field along the geographic north. This is
Sir, I got 2.5 root 3 into 10 to the power minus 5.
that is correct. For that, I can use this formula. In the next question, the cable is along the magnetic meridian, that is along the magnetic north, and current is going from magnetic north to magnetic south to magnetic north, like this. Find force on the wire. So first calculate the magnetic field along the magnetic meridian. Apurva, can you tell me the magnetic field along magnetic meridian?
Sir, 500 into cos 60.
Cos 60 is correct. 5 into 10 to the minus 5 Tesla ना इतना magnetic field है इसका cos 60 लेंगे फिर फोर्स हो जाएगा IL. Current is not given here. Okay, now take the current as 1 ampere. Current is 1 ampere. Then find the force. Pura, tell me the value of force.
Sir, 1 second. Sir, 25 into 10 raised to minus 3.
I will do 500. So 2500. So 2.5 into 10 raised to minus 2.
Yes.
Achha, what if the wire is kept along geographical meridian? So find the magnetic field. And then find the force.
Sir, is it 12.5 root 3 into 10 to the power minus 3?
Yeah, force will be 12.5. I should write 1.25 into 10 raised to minus 2. That is the same thing. And magnetic field, it will be 2.5 into 10 raised to minus 5 Tesla. All right.
Sir, in the previous question for force, why did we not take sine 60?
Sine 60 will give you the vertical direction of force. Now. The wire is along magnetic meridian. So it is along the horizontal direction. So we are taking BH. BH is DE cos delta.
Okay, sir.
All right, moving on to next topic. We'll do some numericals on it after the next class. After you have studied it from the book. I'll be giving you questions in the worksheet also. In the end of this, by the end of this chapter, we'll be solving problems of all the topics that we have studied. This is a big chapter, so we'll be doing a quick revision also. Now, next topic, next portion of magnetism is magnetization. Magnetization, that is the process of converting substances into magnets. How do we do that? That we're going to study here. So, a very simple experiment if you do, if there is a soft iron bar or soft iron piece. So it has been observed that a soft iron, when it is produced from the factory, it is unmagnetized. It is unmagnetized. So it does not has a magnetic field of its own. Okay. Or you can take another piece, which is due by some phenomena which will be studying, it is magnetized. So unmagnetized means the net magnetic field due to its own, that will be zero. But if it is a magnetized soft iron, then it will have a magnetic field of its own. So it will have a magnetic field of its own. Let me call this as magnetic field internal. This is magnetic field internal, or yeah, this is internal magnetic. Now, if I take this piece and keep it in a uniform magnetic, I'll take this whole thing and keep it in a uniform magnetic. So what happens? The magnetic field changes around this region, and this gets even more magnetized. The magnetic field inside increases. These red lines are the new magnetic field lines. So the intensity of the magnetic field, it increases. Now this was the external magnetic field, call it P. This is the external magnetic field. So now we have a total magnetic field inside B total, that will be equal to B external, want to call it B external, plus B internal. This is total magnetic field, B external plus B internal. And this will happen even if the soft iron is unmagnetized. Means when an unmagnetized soft iron is kept in a magnetic field, it becomes magnetized. It becomes magnetized. So to understand this whole process, how this happens, we're going to define some terms. And after we have understood those terminologies, that is the language of this topic, we will come back to how this phenomenon happens. So first term that we're going to, I'll just write the definition. First term is magnetic induction. So induction is inducing. The external magnetic field is inducing a magnetic field in the soft iron. Okay. So what is magnetic induction? The process of magnetization, or the process of a substance becoming magnetized in the presence of external magnetic field. In the presence of external magnetic field is called magnetic induction. So you keep any substance in a magnetic field, it becomes magnetized. The process is called magnetic induction. Okay, and the induced the substance is called the induction, the magnetism produced is called induced magnetism. The magnetism produced this way is induced magnetism. The next definition is of flux density. That is the same thing as magnetic flux. This is the number of magnetic lines of induction inside a magnetized substance crossing unit area, it's per unit area, normal to the direction. It's called the flux density. And it's called the magnetic flux density. And it is also called the magnitude of magnetic induction. Is also called the magnitude of magnetic induction. So jitna magnetic field induced हुआ, that is measured by the flux density. Measured by the flux density. Then substances become magnetized because there are very small dipoles inside the substances. This minus positive, minus plus, or again, if you want to write plus and minus m, then there is small m vectors like this. जिसकी वजह से substances magnetize होते हैं. So to take into account of those, we define this term intensity of magnetization. Intensity of magnetization, and this is defined as magnetic moment per unit volume. So जब हम external magnetic field apply करते हैं, तो छोटे-छोटे magnetic dipoles induce होते हैं, dipoles बनते हैं, and due to that there is magnetization. So intensity of magnetization हम बोलते हैं magnetic moment per unit volume of the magnetized substance. Per unit volume of the magnetized substance. So this is represented by capital M, and because it signifies magnetic moment, it is related to magnetic moment. So we write capital M vector is small m vector per unit volume. This is intensity of magnetization, and small m is magnetic moment. So external field की वजह से substance के अंदर नए छोटे magnetic dipoles generate हो रहे हैं, and to measure that we refer to this quantity intensity of magnetization. The next term is magnetic intensity. And this is also called magnetic field strength. And this is defined as the capability of the magnetizing field. Capability of the magnetizing field, that is external magnetic field, to magnetize the substance and it is represented by H vector. So the actual relation is like this. जो total magnetic field होता है, that is mu naught times the H vector plus M vector. So what was M vector? M vector जो already magnetic field अंदर था, उसकी वजह से जो magnetization हुआ, and H vector जो external magnetic field की capacity है अंदर magnetic field generate करने के लिए. So we can write this as B vector equals to mu naught H vector plus mu naught M vector. So mu naught M vector क्या है? ये already magnetic field था, और mu naught H, this is the external से induced कितना हो, external वाला induce कर रहा है, that is mu naught H. And this is already internal magnetic field, that is B in. So from here, the magnetic intensity के लिए हम relation लिख सकते हैं. H vector can be written as B vector by mu naught vector minus M vector. Books में usually ये represent करते हैं, but I like to remember it using this relation. So you can choose which one to do. Note this. Capital M is intensity of magnetization. That is magnetic moment per unit volume. H is called the magnetic field strength, और B क्या है? B net magnetic field है. B is the magnetic field induction inside the substance.
And what is M?
M is magnetization, intensity of magnetization. Here, third वाले definitions.
और fourth वाले में?
Fourth वाले में भी same ही चीज है. M is intensity of magnetization. Intensity of magnetization जो अंदर magnetic dipoles है उन पे depend कर. So that is responsible for internal magnetic. And B is total magnetic field induction inside substance. B को हम कह सकते हैं total magnetic field. तो अंदर वाले का सम प्लस बाहर वाले से जो इंड्यूस हुआ, दोनों को मिला के. Okay. After this, the next thing that we're going to define is the ratio of B vector and H vector. This is called the magnetic permeability. So what is B vector? B vector is magnetic induction. B vector is magnetic induction. And H vector is called the magnetic intensity. सिमिलर सा नाम, थोड़ा टाइम लगता है ये याद करने में। H is the magnetic intensity, एंड इन दोनों का रेशियो हम बोलते हैं इक्वालिटी मैग्नेटिक परमिएबिलिटी और एब्सोल्यूट मैग्नेटिक परमिएबिलिटी. दिस इज मैग्नेटिक permeability. Okay, ratio of magnetic induction to ratio of magnetic induction, that is B vector, to the magnetic intensity I should write magnetic induction induction inside the magnetic substance. अच्छा, बार बार मैग्नेटिक इसलिए लिख रहे क्योंकि इलेक्ट्रोस्टैटिक्स में भी ऐसा एक टॉपिक होता है, that we call it as induced charges. So वहाँ पे भी similar mathematics होती है, but that's not in your syllabus. Ratio of magnetic induction B vector inside the magnetic substance to the magnetic intensity. To the magnetic intensity. And that is H vector of the magnetizing field. So if you want to write it the actual value of mu, I should put a mod because just write mu is equal to B by H. Then after magnetic, this is absolute magnetic permeability. So vacuum ke liye this value is 1. So for vacuum, no, for vacuum, the ratio is mu naught. For vacuum, mu is equal to mu naught. And after this, we define relative magnetic permeability. Relative magnetic permeability. This is the ratio of magnetic permeability of the substance to magnetic permeability of the free space. Ratio of magnetic permeability of the substance that is mu to the magnetic permeability of free space. Permeability of free space. And this is a dimensionless quantity. Relative magnetic permeability is a dimensionless quantity. After this, we define magnetic susceptibility. And this is the ratio of magnetization to the magnetic intensity. And we like to write it like this. Magnetic susceptibility is written as this. This is called psi. Psi, again a Greek letter, psi. So this thing is the ratio of magnetization ratio of magnetization, or also written as intensity of magnetization. Intensity of magnetization, that is your M vector, to the magnetic intensity of the magnetization. Magnetizing the magnetic intensity of the magnetizing field. So magnetic intensity is your H vector. This is your H vector. Magnetic intensity of the magnetizing field is H vector. So M vector and Xi vectors are related like this. But we also have electric susceptibility. So that's why I'm writing as Xi M. Xi M is magnetic susceptibility. Note this down, then I will relate all these quantities.